In the vast and mysterious universe, a single event has defined our understanding of everything we see: the Big Bang. But what if this foundation of modern cosmology is not the complete picture? What if, beyond the veil of known physics, the universe hides a secret history of cycles, of endings that are beginnings, of collapses that give birth? Join us as we unravel the fabric of space and time, exploring the provocative idea that the Big Bang was not the beginning but simply a chapter in an endless cosmic story. Most of us are familiar with the conventional story of how the universe began. There was an infinitely dense point of infinite temperature and indeterminate size, called a singularity. This singularity exploded, creating all the space, energy, and matter we know as our universe in an event called the Big Bang. Between 10 to 36 seconds and 10 to 32 seconds, space expanded exponentially, becoming much larger. After this period, space continued to expand, but at a much slower rate, and we eventually saw the universe we observe today. This is the inflationary Big Bang theory, the most popular and widely accepted theory of how the universe began. However, for some physicists, the dominant theory does not give an accurate picture of how our universe evolved. Rather, they argue that the universe existed before this moment, expanding infinitely into the past and future. While the universe is expanding today, it was contracting before the Big Bang. In this picture, the Big Bang is not a bang but a rebound, the moment when a contracting universe reversed course and began to grow. According to their theory, the universe could bounce back. Today's expansion could be followed by a collapse in the distant future, followed by another rebound. Some physicists think this rebound could be infinite. Of course, this goes against the view of most cosmologists that everything began with the Big Bang. But what's worth noting here is that this theory isn't the only one that dares to question the cutting edge of cosmology. Renowned physicist Brian Cox has also questioned the Big Bang theory, saying that something cannot come into existence out of nothing. Adding to the tension, the James Webb Telescope has made a series of surprising discoveries that contradict the idea that the Big Bang marked the beginning of the universe. All of these discoveries beg the question: if the Big Bang wasn't and isn't the beginning of the universe, then what is? Could the universe have begun with a turning point, or something else entirely? Let's take a closer look at one of the most thorny topics in physics: the idea that the universe had a beginning, or the day without yesterday, as it was originally called, was first proposed by Georges Lemaitre in 1927. While it is still defensible to assert that the universe may have had a beginning, this period in our cosmic history had very little to do with the fiery Big Bang that characterized our early universe. Although many laypeople and even a handful of experts still cling to the idea that the Big Bang marked the beginning of everything, this definition is outdated. Today's Big Bang was not the birth of time and space. We know this today, in 2023. In fact, there is a lot of evidence pointing to a non-unitary origin of our universe. We have never reached temperatures this arbitrarily high. There is a limit. Instead, our universe is best described by a period of inflation that preceded the Big Bang, and the Big Bang was a consequence of what happened at the end of the inflation. Let's see what it looks like. During inflation, the universe is completely empty. No particles, no matter, no photons, just empty space. This empty space contains an enormous amount of energy, with the exact amount of energy fluctuating slightly over time on average by about 1 part in 30,000. As the universe inflates and expands rapidly and inevitably, these fluctuations expand to larger scales while new small-scale fluctuations are created above them. The superposition of small-scale fluctuations on intermediate scale on large scale on superhorizon scales is one of the defining predictive features of cosmic inflation. This phenomenon continues as long as inflation continues, but it stops randomly and not everywhere at once. In fact, if you lived in an expanding universe, you would probably experience a neighborhood where inflation ended while the space between you and it expanded exponentially. For a brief moment, you might even be able to detect what was happening at the beginning of the Big Bang before that region disappeared completely from view. In a relatively small initial region, perhaps no larger than a human-sized hamster ball, but probably much larger, the energy that was in space was converted into matter and radiation. The conversion happened relatively quickly, taking about 10 to 33 seconds, which is short but not instantaneous. As the energy contained in space itself changes into particles, antiparticles, photons, and the like, the temperature begins to rise rapidly from a few degrees above absolute zero to about 20 Kelvin or so in this same short time span. Because the amount of energy being transferred is so large, everything will move at close to the speed of light. Every quantum will behave like radiation with some inherent kinetic energy, whether the particle is massive or massless. It doesn't matter under these conditions. This transition is called warming and means that inflation ends and the phase known as the hot Big Bang begins. In terms of the rate of expansion, you will see a huge change from any previous behavior when the hot Big Bang begins. In an inflationary universe, space expands exponentially, with the most distant regions moving ever further apart over time. But when inflation ended, the universe heated up and the Big Bang began. The most remote areas are moving further and further away over time. From an external perspective, the part of the universe where inflation ends has a reduced expansion rate, while the expansion regions surrounding it do not experience such a decline. Under inflation, the distance to any object will double after a certain amount of time, and when the same amount of time passes, that distance will double again, over and over again. This process is relentless. But once the Big Bang started, all that changed, as the expansion of the universe immediately slowed down. Once the initial expansion had passed, it was likely that from the perspective of the expanding region of space you were in before the Big Bang, you would see inflation ending many times in the vicinity. The places where inflation ended would quickly fill up with matter, antimatter, and radiation, and would expand more slowly than the still expanding regions, leaving you in the expanding region as a typical region of space-time, dominating its volume. These hot Big Bang regions would expand away from all the other places where inflation continued exponentially, meaning they would move away from each other very quickly in the standard inflationary picture. 006. Because of this change in the rate of expansion, it is unlikely that two universes with separate hot Big Bangs will collide or interact. Eventually, the region we are about to live in is cosmically lucky, and inflation will end for us. The energy inherent in space itself will transform into a hot, dense, and nearly uniform sea of particles. The only imperfections and deviations from uniformity correspond to quantum fluctuations that existed and permeated the universe during inflation. Positive energy quantum fluctuations will correspond to regions that were initially too dense, while negative energy fluctuations will transform into regions that were initially too dense. But this is still enough to serve as a seed for the structure of the universe. We cannot observe these density fluctuations today, as they did when the universe experienced the hot Big Bang. We do not have access to the visual signature from this ancient time. The first planet we encounter is 380,000 years later, after these planets have undergone countless interactions. Even at this time, we can extrapolate the initial density fluctuations and find something that fits perfectly with the inflationary history of the universe. Temperature fluctuations imprinted on the earliest image of the universe, the cosmic microwave background, give us confirmation of how the Big Bang began. However, there are many inconsistencies between the cosmic microwave background and our current cosmological model. We are missing something. This can be summed up as an anomaly. First of all, on very large scales, the universe does not work as we think. Second, light from the cosmic microwave background would be reflected by the material between us and the cosmic microwave background. This means that the material would act like a giant lens, bending and changing the amplitude of the light behind it. The frequency with which this happens is inconsistent with our current model of the universe. This is such a big problem that it is sometimes referred to as a crisis in cosmology. Third, the two hemispheres of the cosmic microwave background sky have different average temperatures. This doesn't make much sense, because we think the universe should have started out uniform on average. And finally, the value of the Hubble constant, which describes the rate of expansion of the universe, is different depending on whether we measure it from the cosmic microwave background or from the more nearby Cepheid stars. Taken together, these anomalies mean that we're missing something fundamental in our understanding of the universe. The answer may lie in loop quantum cosmology. Loop quantum cosmology arises from loop quantum gravity. In loop quantum gravity, gravity itself is made up of particles called quanta. These quanta combine to form the fabric of space and time. In this model of the universe, there is a smaller spatial scale, the Planck scale, or 10 to 35 meters. Nothing, not even space, can be smaller than that.